So let's get going. I wanted to talk about a couple of administration issues. So the first thing is the schedule's up for the rest of the quarter. Monday, May 27th is Memorial Day, which is a holiday. So what I'm proposing that we do is instead reschedule that class for Tuesday, May 28th. Does that not work for anybody? Doesn't work for you?
Oh, I just have to go figure something else out for parking.
That's solvable.
Yeah.
You've got a class conflict? How many people have class conflicts or other conflicts on Tuesday? Okay, let's try the rest of the week. How many people could make it on Wednesday? Or how many people could not make it on Wednesday? That's easier. Okay, how about Thursday? Any hands up right there? Okay, so just to do the two-phase commit, I propose we reschedule class for Thursday, May, whatever that date is.
30th.
30th, thank you. I can add. No discontent? Okay, we'll do that. Thank you. Another piece of administrivia, I got an anonymous email about the discussion board, which was really helpful. Basically saying that given the volume of posts and replies, it's getting confusing to track the sub-threads within each paper. So I'm trying to figure out what to do about that. Here's one concrete proposal. I could, instead of having a discussion thread per paper, I could have a discussion thread per question per paper. What do you think? The downside of that is there will be 12 threads each week, which starts to get a little bit confusing. But the upside is at least the request for response thread should be self-contained within a single discussion board now. I gotta get used to looking at the Microsoft folks. Sound okay? Okay, we'll do that.
So in that case, should we answer all 3 questions within the paper, or?
No, it's still pick any question that you like.
Okay.
For 2 of the 3 papers. So you only have to pick 2 of the 9. 2 of the 9 in order to respond to. Okay.
So what if you have the unique answer, which is not answering any of the 3 questions?
I guess I could do 4 discussion threads per paper. question, other. I'm happy to do that. So let's do that. I'll fix that for next week. So I'll delete the discussion threads that are there for next week's and replace that with 12 ones. This is going to get unwieldy, but that's okay. Homework number 1. How many of you finished? Ooh, what was your clock skew?
Oh,
per
I
second.
know, about 300 milliseconds an hour or something.
So that's about 10 microseconds a second.
58.
Oh, 58 per second. How about you? Oh, okay. Yeah.
When I ran it for an hour, I saw 16.
16 microseconds per second? Yeah.
I got minus 26.
26.
Minus 28.
Minus 20. Ooh, were you on the same computer? That's interesting. So mine was about plus 70 microseconds. So all of these are about what I was expecting. So for those of you who haven't done it, if you see clock skews are significantly less than that, that probably means that you haven't turned off clock synchronization on your computer, and it's being forced into synchronization with NTP. There was a couple of questions, one on the discussion board and one sent to me directly, about what accuracy do you have to gather timestamps for. And the issue is on Windows, if you use my suggestion of Python's time.time, you only get millisecond accuracy. So let me pose the question to you. Given what you've read in the assignment, what accuracy timestamp do you need in order to satisfy the assignment?
Microseconds.
Why?
Because we get too much of a clock.
But if you're measuring over 12 hours, that's okay. This is really minutia. One of the things that I asked for is this histogram, which is basically a histogram of the individual clock skews that you measure for each measurement. And if your clock timestamp is only milliseconds, and you actually have on the order of 20 microseconds per second clock skew, you're not actually going to be able to measure that in an individual interaction with the server. So if you're using Python on Windows, you'll have to figure out something other than time.time in order to pull it off, in order to generate a meaningful histogram for that. Last piece of administrivia is, I always have to be reminded of this, that for those of you who are fifth year masters, you registered for a different course number than the PNP students, and that means you're not automatically added to the class mailing list. So for those of you who are fifth-year masters, if you haven't yet, please ask me to manually add you to the course mailing list by sending me some email. And I'll make sure that I do that.
What about the link on your site? Can you not sign up?
Well, you can do it that way too, sure. If you directly have added yourself, that should be preserved. So that's another way of doing it. Okay, let's talk about the papers for this week. I love this set of papers. It's some of my favorite. I wanted to start by talking about the physical clock synchronization topic, so NTP. And I guess I wanted to start by asking, what's the goal of clock synchronization? Simple question, so hopefully a simple answer. It always is, right?
To make sure that all the computers in the system observe the same time, well, roughly the same time.
How roughly?
However we want, we can pick.
Milliseconds.
Yeah.
Milliseconds.
Why that's an interesting answer. Why milliseconds? Is that because that's the best you think we can do, or because you think that's good enough?
I think that's best.
So the contention on the table is milliseconds of precision, milliseconds of accuracy is the closest that we can get with clock synchronization. Who believes that?
Over the network.
Over which network?
Over the network.
The networks of
The wide area or local area within a cluster?
Wide area.
So that's interesting. So why is it that wide area latencies lead to millisecond accuracies for
So the
NTP?
CTL,
Say it again?
the CTL, if you want to synchronize computers, you have some delay between to send the messages and it's milliseconds.
So the round trip time, the RTT, will be on the order of milliseconds. But we'll get into this in gory detail soon, but is there any intuition for why you think the round trip time bounds the accuracy of clock synchronization?
It's the variability of the round trip time. If the round trip time was exactly predictable every single time, then you wouldn't have that be a bound for your synchronization accuracy. But if you can't tell how much time existed between, or basically the difference in time between how long it took your message to go to the server and the server's message to come to you, that the change in those two times are basically what kind of bounds the accuracy of your synchronization.
Right, so that's good intuition. So the thought exercise is, if the round trip time were precise and symmetric and known, then there's a really easy way to get perfect clock synchronization, right? Which is basically, I send a what time is it on your clock, you send back what time it is, and because I precisely know the delays on each direction, it's a simple arithmetic to figure out the offset between the two clocks. So there's something about the distribution of times, of round trip times, that starts to make it harder to get clock synchronization. And we'll come to that in a second. So one of the things that we already sort of positing is that the way to do clock synchronization is to have a clock master that somehow is keeping the best possible time out there, and then to have a bunch of clock slaves that are interacting with that master in order to do clock synchronization. So let me ask this. What does it mean for the clock master to be a correct clock? If slaves are synchronizing off of that master, they're assuming something about that master, presumably.
The master has to sync with the reference
And how does it do that?
by using the same communication method, possibly.
Potentially using the same clock synchronization protocol, but to some authoritative
Some
time
authoritative
source.
time source.
And what does it mean for a time source to be authoritative?
It's regulated by the government.
Somebody declares that this is actually the current time, right? So I don't know how many there are, but there's a very small number of authoritative time sources per country or per the entire globe that are mandated to be the current universal time coordinate. And those are kept to be incredibly precise using atomic oscillators and things like that to get a very bounded skew of that particular clock rate. So somewhere, at some particular point in time, somebody blesses a certain clock to be authoritative time, engineers it so that that time is incredibly regularly kept using physics, and then treats that as the authoritative time source for everybody else. Okay,
Okay, so that gives you this incredibly accurate absolute time,
Yep.
which I would tell you in most cases in the engineering systems I've worked in is not nearly as important as, say, everybody agreeing that the time is the same, whether or not it's right in any absolute sense, sort of who cares, as long as me and the domain controller agree within 5 seconds, I can log in.
So there's two properties we might end up wanting from clock synchronization, and you just mentioned both of them. One of them is internal consistency, which is if you've got a collection of clocks that are mutually synchronizing with each other, those clocks can all be accurate with respect to each other, and that's internally consistent. Another one is external consistency, which says my clock is accurate to universal coordinated time. And both of those are possible. The only thing to think about there is external consistency gives you internal consistency, but the opposite isn't true, obviously. Okay. Let's say I'm a slave clock. What does it mean for my... So I'm basically have some sort of hardware clock that has a certain property with respect to its continuity over time. And I'm trying to adjust it so that that clock is in sync with the master. What does it have? What property do I need for that slave clock to be considered correct? Is there any behavior of clocks that would throw things off completely? Or
Jumping backwards in time,
why?
because if you have processes that are expecting time to increment, time suddenly decrements, then they throw off calculations.
So one thing that's probably got to be the case is time progresses monotonically. And if it's not the case, then you might end up with a negative measurement across a certain time interval, which could break a whole bunch of code. That's a potential issue. Is it okay for my slave's hardware clock to drift? In other words, to proceed at a rate that's different than the master's hardware clock?
It's not desirable, but if you sync frequently enough with a server with an authoritative source, you might offset it to some extent.
So paraphrasing, yes, it better be okay.
Yeah.
Because if I implement a clock and you implement a clock, our clocks are going to proceed at slightly different rates. Why?
Physical properties of the clock.
Like what?
Crystals are not the same.
Differences in the actual product.
Yeah, so manufacturing defects, basically.
Temperature is a bigger one.
Temperature is another issue. So all of these are with respect to clock crystals. Does anybody know how those work?
Chemistry.
Yeah.
Physics or chemistry or the combination of the two. They are magic. But roughly the way to think about it is a clock crystal is basically, quartz crystal has this property called piezoelectricity, which and I don't know a lot about this, so I'm going to be doing the best that I can here. But roughly think of it as this lattice of atoms, and that entire clock crystal can oscillate. So the distance between them can fluctuate, and there's a whole bunch of different ways that it can oscillate, but there's some dominant mode that it likes to mechanically oscillate. And if you started oscillating in that dominant mechanical mode, the fact that it's oscillating actually causes a little miniature electric field as a result of that. If you measure that electric field and then amplify it back in, then applying an electric field to that actually accelerates that oscillation. So basically, by introducing a feedback loop into this mechanical device, you can basically get this crystal to oscillate according to its dominant mode and to produce an oscillating electric field according to its dominant mode. And that's basically now a regular signal that you can then use to drive a clock. It's basically like that, exactly. So, so here's the issue. Different sizes of crystals or shapes of crystals or defects inside of the crystal structure can cause it to have a slightly different dominant oscillating mode. So unless you produce exactly down to the molecule the exact same crystal, they're going to vibrate slightly differently, even though they're pretty similar to each other. So that's one of the mechanical things for at least quartz crystal oscillators that will cause them to have subtly different clock rates. And then your point was temperature is another factor. Temperature, it turns out for these things, does affect the rate at which it will mechanically vibrate. Luckily, it's not a linear effect, it's a sublinear effect, which is why people choose that material.
Yeah, well, and when they design the circuits, if you care about that, they'll actually put them in little heaters
Oh, really?
You control the temperature of the oscillator so that it'll in some sense be stable.
Now you just need an accurate thermometer, which is a whole other discussion.
But somewhat easier to pull off.
I believe it. Okay, so
Well, actually more in the sense that if you can get it consistent, right, you can tune these things. Because you can measure it's easier to measure the frequency than it is to get it right, so you can tune the circuit.
I see. Okay, so what we basically just talked about is clocks basically drift according to some rate. And I'm going to be throwing some equations at you throughout this part of the lecture, so sorry about that. But the way to think about it is a slave clock should be assumed to be correct if there is a known drift rate that it stays bounded in between. So if I measure the time according to my clock right now, then I wait delta and measure it again, then the difference in those clock readings ought to be delta times the 1 minus the drift rate, or delta times 1 plus the drift rate. So a correct clock never drifts more than plus or minus that drift rate. So is it possible to have an incorrect clock? Sure, of course. If the temperature fluctuates wildly or the crystal fatigues for some reason, I don't know if crystal fatigues, but maybe it does, or other things like that, then that clock can actually drift at a more aggressive rate than its manufacturing tolerance. But roughly what we're going to assume is that there is a bounded and known drift rate for each clock. Okay. So I'm going to propose a clock synchronization algorithm, and I want you to tell me how much you like it or don't like it and why. So the master clock, which is the authoritative time source, periodically broadcasts, using whatever broadcast medium it has. The time is now X. And when my slave clock receives that broadcast, it just sets its local clock to time X.
It's a bad actually idea because
It's a bad idea.
you don't know like how long it takes until the broadcast reaches you from the master clock.
What if I assume, since it's a radio, that it's speed of light?
But in one particular instant, it will be too odd.
Say it again?
One particular time of synchronization, it will be too, the time will be too longer than the normal time, and you can't just set it to that.
So one thing that I'm guaranteed is that that speed of light delay is non-zero. So if I set my clock to be what the master broadcast some time ago, my clock's guaranteed to be off. So how far off could it end up being?
Speed of light.
Distance over speed of light. So that,
Processing.
and that's assuming that
In most
speed,
cases.
in most cases, and that's assuming that speed of light actually bounds the signal propagation. If I have Wi-Fi,
Well, there's also bandwidth considerations because there's got to be a high enough frequency to detect the change. And so
say more. I don't think I understand.
you're talking about communicating over radio, and so the bandwidth of your signal is dependent upon the frequency that you're transmitting at.
So the rate at which I can encode the time itself.
Yeah. Well, and how much time has to happen before you can detect a change in the modulation of the signal?
Oh, I see.
Less at higher frequencies because.
Fair enough.
These are all bounded, right?
These are all bounded.
Yeah.
So the bigger risk is that you might set your clock to the past because you were.
You're
going
guaranteed to
past.
set it to the past.
No, what I mean is
Oh, I see.
you are T, you are a particular T, and you get a broadcast saying the real time is T less than T. So you would set your own clock to
Oh, I see. So this
Fast.
doesn't guarantee monotonic increase in clock.
on your clock.
Let's ignore that for a second. Does this, so one thing that we hypothesize is if we do this using radio propagation, maybe we can precisely know or bound or make regular the signal propagation delay.
Yeah,
If I-
GPS. So start by using more than one radio because you don't know what your distance is. You end up building GPS, right? We've got very accurate clocks spinning around in the heavens, and we can look at the difference in the signals from more than one to get our distance and therefore
Yeah,
the
GPS is
delay.
interesting. We'll come back to that, so hold on to that thought. Does this proposal give you internal consistency between multiple slave clocks? Why not?
Because they're not talking to each other, that they're only talking to the,
But they're not talking to anybody, they're just listening.
yeah, well, they're only communicating with the master of the clock, they're not
each other. So
But why does that not give you internal consistency? Yeah,
Their distance to the master might be different.
exactly. So my clock might be further away than your clock. I don't actually know how far away my clock is, let alone the difference between my distance and your distance. So there could be unbounded differences depending on how far away those clocks are.
It beats the heck out of no synchronization at all. You probably are going to get anything, if the master was on the moon and we're on Earth, we're going to get within a second of each other anyway, right? And that's still better than what you get after 12 hours with no synchronization.
It's true. The drift rates that you're measuring imply 1 or 2 seconds of drift per day, which is interesting if uncorrected for your current clock oscillators. So that's really interesting. Okay, let's say that it's not radio propagation, but I'm doing this broadcast over the internet.
Then it could be held.
Same problems.
Which problem?
Variable latency between every node and the master.
So one
now it
problem.
can be unbound.
So,
Unbound, yeah.
so the
Previously,
factor.
it wasn't unbound.
Previously, it was bounded by speed of light,
Oh,
but now
it was unbound.
Well, it was still unbounded because there's no guarantee you're going to receive the signal when it's sent even over the radio.
fair enough. I could be infinitely far away too, but let's ignore that problem. Okay, so a couple of issues come up. One thing that you say is, just like with radio propagation, message delivery time on the internet depends on topology and other factors.
Topology, network stability.
So 2 different clients on the internet will receive different round trip times to the master. Different minimum round trip times to the master. Another problem that you're saying is, even if I just focus on one clock receiving a broadcast from the master, the propagation delay of that broadcast will fluctuate from broadcast to broadcast, just because of internet factors like congestion and so on. Why does that cause a problem?
Now you cannot satisfy that
Because what?
because the propagation of the time sync message could be delayed arbitrarily long because there is no guarantee of message delivery on the internet. It could take a day. I mean, it will not take a day.
There's a very, very small probability that it will take a day,
Right.
but it could. More realistically, it'll probably take close to the minimum time most of the time, but then have factor of 2, 4, even 10 or 20
Yes.
increase in latency depending on how unlucky you end up being. Okay, so this unpredictability in the bounds at which messages are delivered starts to cause a problem. So can you think of a way to fix a broadcast-based system so that it doesn't have...
Depends on the location. If you just cluster them together for the location, the distance-wise, then you have higher chance of getting that message back in short amount of time.
So I think what you're saying is, if I'm a slave, I should scribe to a master that's close by me. Or are you
Yeah.
saying that multiple slaves should be close to each other and then they'll be internally
All
consistent?
of them should be close to each other. So the master should be close to the slave, and the master should get that. Well, the master can also act like a switch for the other master, right? So the other master might be other.
So I like 2 things that you did. One thing that you did was say we should try to make as small as possible the propagation delay. Because what we discussed earlier, and we're going to get precise about that, is that propagation delay bounds the accuracy to which I can do synchronization. The second thing that you did, which I really like, is you introduced the word probabilistic to this, which is cool. So one of the things that you might think of trying to design is a deterministic clock synchronization algorithm, where every interaction with the clock master causes me to adjust my clock. But in fact, another way of doing it is to interact with the master, observe some property of that interaction, and if I like it, then adjust my clock, and if I don't. So depending on my if I like it criteria, I can tune the probability with which clock synchronization succeeds and make it more accurate or less accurate depending on how I tune that probability. So we'll come back to that idea in a second. Okay, so one of the things that sorry. One of the things that I wanted to do is
Are the routers designed to have better quality of traffic like this protocol?
no. Routers do not favor NTP traffic over other traffic. Should they? No. A lot of people are shaking their heads no. Why do you say no?
It's privacy.
Privacy?
Yeah.
I didn't expect that. Say more.
Well, I mean, just that if you start emphasizing one type of traffic, then people can exploit that.
Yeah, denial of service might be one issue.
So one way that I could exploit that is if I'm an unscrupulous protocol designer, I'll encode all of my protocol messages for peer-to-peer file sharing traffic as NTP messages and get better quality of service than everybody else. But generally, this is a really contentious topic and for a networking, the domain of a networking course. But should we have higher quality of service for some protocols than others is incredibly contentious. There's no good answer to that question.
I thought net neutrality was the only acceptable answer to that question.
I plead the fifth on that one. I'm not going to be tricked into that debate because I know whichever side I pick is the wrong side. It's one of those kinds of debates. Okay, so basically what we decided is the reason that clock synchronization can end up being hard in practice over the internet is because the propagation delay basically is probabilistic and it looks something like this. So here there are three features of this that I claim are relevant. One feature is that there's a minimum propagation delay. The second is that there's a mode, a most common propagation delay that you're likely to get that's slightly higher than the minimum. And the third is that there's a infinitely long maximum. So somebody walk me through those three features and tell me why this must be the case. Why is there a minimum?
Speed of transmission.
What's the difference?
Well, you're transmitting over copper wire or whatever the transmission
Oh, I
is,
see.
which is going to be slower to transmit electrons than.
Right, the speed of electromagnetic radiation in copper is slightly less than
Plus the
free space.
processing on each of the nodes, which could be bound, but that's the.
Plus you have to spend some time encoding the bits onto the wire. So the longer the message, the longer it takes to actually dump the message onto the wire.
And
Plus
the more
routers
routes-
along the way have to process that message. So there's processing delay inside of each hop along the way and so on.
Software and hardware.
Say that again?
Both the software stack and hardware stack also.
Yeah, exactly. And there's minimum software processing delay on both the sender and the receiver and so on. Is this minimum propagation delay something that can be measured or known?
It could be measured probabilistically if you can take whatever minimum you observe and take that as your first order guess of what the minimum likely is on that route.
Should I say it a different way? Would it be safe for me to design an algorithm assuming a certain measure of minimum?
If you know the network well enough.
Say that again?
If you know your network very well, you know that two computers, for example, are always going to be at least this distance apart from each other, and the transmission line that they're sent on can be, faster than this, then you can say an absolute minimum. But if you don't know the network, then you can't really assume a minimum.
I think that's right. So if you can very precisely engineer and control and keep constant everything about the computers and the network in between them, then it might be the case that you can calculate or measure a minimum and be safe on that. But for instance, if we were to measure a certain minimum across the wide area, then there's no guarantee that that minimum will remain stable across time. Because for instance, internet paths, the routes that packets can take, can change over time. So you've got to be really careful about assuming anything about a minimum. The second property that I said is that there is a mode that's usually slightly higher than the minimum. Why is there a mode and why is it going to be higher? Said a different way, why isn't the mode the minimum?
Because you're not the only one transmitting the network. You might have congestion.
So there might be even relatively small amounts of queuing at the routers along the path that you're taking. So if you've got the network entirely to yourself, you might have a chance of your mode being the minimum. But as long as there's other customers or other classes of traffic that you're contending for that wire flow, that's enough to bump you up slightly above the minimum. Plus, the very best possible processing delay on the end node isn't the delay that you'll end up experiencing most of the time because of things like cache misses inside of your processor or page faults and things like that. So all of these engineering considerations bump you slightly above the minimum.
Just the quantization will cause this.
Fair enough. Yeah, I think I understand what you're saying. That with the quantization of bits on the wire.
Well, yeah, I mean, your computer just does things at certain intervals, and you know, even if the signal changes on the wire, you're not going to observe it until the next clock tick of some clock on your
right. But now we're talking about individual signal propagation or symbol propagation delays. But fair enough. We talked about this a little bit last week, but I want to ask it again. Why isn't it safe to assume a maximum?
Message might never arrive.
Oh, one reason is packet loss. Let's assume that we have a perfect error detector that tells us if packets have failed. Clearly you can't build such a thing, but I'm just trying to rule out one reason and see if there's other reasons.
I mean, you might just have a node that's collecting packets and eventually it will send them out. So at no point are those packets failed, but you can't determine when that node that you have no control over will release those packets.
Right. If there's a configuration error or a malicious node, they could buffer and then retransmit packets arbitrarily. The case where you typically see extraordinarily high delays is if there's a routing loop inside of the internet that only persists for a little while. So packets can get trapped in that loop, and eventually when the loop repairs, out they go. Incredibly rare, but it can happen. Okay, so what I wanted to do is actually start a little measurement, and somebody remind me after the break to stop the measurement. But I'm going to actually try, just for kicks, seeing if we can collect one of these histograms and seeing how close it is. So this is measuring 10 times a second. I'm going to pipe that to a script that just strips out the individual seconds. And I'm going to stream that to a file. Let this run for like an hour or whatever. So somebody remind me to come back and collect and plot that near the end of the quarter, or near the end of the lecture. Okay, so one of the things that we proposed is a broadcast-based time synchronization. One of the issues with that is variable propagation delay of messages. Not only that, that propagation delay is unknown to the receiver, so it has no way of compensating for that. So if we wanted to try to engineer a protocol by which the receiver actually tries to estimate and compensate for that propagation delay, how would we do that?
You make them location aware.
If this is radio broadcast, then I think that's right, and that's roughly the path that GPS goes down. Let's say that we're doing this over the internet.
The slave starts to send stuff as well to measure the RTT and average it out over time to understand the delay.
So I like that suggestion. So basically what you're saying is, instead of being a passive receiver, the slave now actually has to interact with the master in order to measure the properties between the slave and the master. So this basically gets us to an entirely different class of protocols, one in which the slave is actually interrogating the master and measuring the interaction response time between it and the master. So that's basically what you read about in the NTP paper. And kind of the way to think about that is, folks at Microsoft, can you see the slides?
Yes.
Excellent, good. So this is basically what that looks like. So over here in this diagram, there's two timelines. The way to read this is time flows to the right. And both the master and the slave each have their local clock. And at slave's time t0, that slave sends an interrogation request to the master. When the master receives it at master time t1, the master immediately sends back a response containing t1. And then that response propagates over the network back to the slave, and the slave measures it at time t2. So this is basically how all time synchronization protocols work, is some variation of this. So when you say it this way, the goal of the slave is to figure out at time slave T2, what does master's clock say? So it's basically trying to figure out at slave's clock T2, what does master's clock read at that particular moment in time? Because if you know that, then you can calculate the offset between the clocks and compensate for that just by doing the simple subtraction between the two. Okay, so how do you do that? How does the slave figure out what the master's clock says when the slave's clock says T2, given one of these interactions?
We can do an approximation that alpha is equal to beta, so the T1 would be exactly the middle of the period.
So if we assume that the propagation is symmetric, which basically says alpha equals beta in this diagram, then that says that T1 lies precisely between T0 and T2. In which case, since we've measured T0 and T2, T2 minus T0 over 2 is the difference between master's T1 and slave's T2. I said that kind of quickly. Does that make sense? Okay. So if you assume symmetric delays, then you can get an exact, you would know precisely what the master's clock says when the slave's clock says T2. It says T1 plus half of T2 minus T0. Okay, so that's good. We just invented a new clock synchronization protocol. Where does it go wrong?
You have non-symmetric.
And non-symmetric delays, and why does that mess things up? This is obvious, but hopefully. But go ahead.
You're assuming T1, measuring T1 is, I guess, are they sending T1 back? Or are they just...
Yeah, the master, when it receives the message, stuffs T1 into a packet and sends it back. That's what the reply is.
There could be a delay in that process.
So one possibility is the master actually takes non-zero time to receive a packet, realize that it's NTP, grab a timestamp, stuff that into a packet, and send it back on the network. And that processing delay could be variable. So in the actual NTP paper, they separated out it into 4 timestamps. So the master receives the packet and the timestamp when the master sends the response in order to try to compensate for that a little bit. Let's ignore this issue for a second. Assume that the master can receive, timestamp, and send a packet instantaneously. So why does the asymmetry cause a problem?
So I have a question here. If there is no delay on the master, then slave could easily compute whether it's symmetric or asymmetric, right? Because all you have is T0 and T2 and T1. You have, like, the slave at T2 will have all these 3 timestamps.
Yep.
And it can measure, like, if it is symmetric, then T1 minus T0 has to be equal to T2 minus T1.
Only if the slave is actually synchronized properly, and if you were synchronized properly, then you wouldn't need to talk to the master in the first place.
Right, so if the slave has some unknown offset between its clock and the master's clock, then you can't do that. And the goal of time synchronization is to exactly figure out what that offset is. So I like that idea, but you've got a bootstrap problem. You need to be synchronized in order to synchronize.
If it's not symmetrical, you just have no idea where T1 is between T2 and T0.
So that's interesting. So if it's not symmetric, if it is symmetric, then you know it lies at the midpoint. If it's not symmetric, it might not lie at the midpoint. But I want to press you on that. You said it has no idea where.
It's probably a distribution.
So it's definitely going to be a distribution.
Depending on what beta and alpha are like.
But the distribution is actually going to depend a lot on the properties of the channel that you're on. So for instance, for my cable modem, my upload latency and my download latencies are actually different. So if I was running this over my cable modem from home, it would definitely be persistently asymmetric. And this is a hard question. Can I measure that?
You can trace around and see how many hops are going through, or you send to the master and then see how many hops to come back.
So I could measure differences in the path the packet takes, but even if the path is the same, from me to you might be a different latency than from you to me, even if it's 1 hop. It certainly is over cable modems. So this comes down to no, there's no easy way of measuring one-way propagation delay unless you have synchronized clocks. There are problems we're trying to synchronize the clocks, so we don't have those. Okay, but to come back to this, you're right that this asymmetry means you don't know that it's in the middle, and it could be off in the middle. You said you have no idea where it lies between T0 and T2. Is that really the case?
I would say it is the case on your first attempt.
If you a priori know what min is, then you can bound it to T0 plus min to T2 minus min.
Right.
If you have no idea what min is, then I think you're right. It can be anywhere between T0 and T2. So in the worst case, T1 happens at T0. In the other worst case, T1 happens at T2. So all of a sudden, the range of offsets is exactly the round trip time.
And if T0 to T2 is a really large number for this round trip, then your uncertainty is increased.
And if you're unlucky and you happen to get a very large round trip time, then your error bound is even larger than you think, or it's bounded by that round trip time. Yeah. Okay, so to do the math on this, I'm going to run through these equations really, really quickly because they're boring, but they're easy. And I'll post these slides afterwards. So if alpha equals 0, mumble, 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 the clock at the master is going to end up being this equation over here. If beta equals 0, then the clock at the master is going to be that equation. You subtract these two, and what you end up with is the error, the maximum error that your offset calculation can be is this, and you achieve that error, you minimize that maximum error if you pick the midpoint between T0 and T2 for your clock estimate. So the best possible strategy that you have is to assume that the propagation delays are symmetric, pick the midpoint, and that minimizes the maximum error between either side. And if you do that, you end up with this maximum error on your calculated clock offset. Just to grok a little bit more math in there, so far this is ignoring clock skew. Clock skews. In other words, my clock might be proceeding at a different rate than the master's clock. So if you do the math and factor that in, if you assume that you know the difference in clock rates, then you end up with an equation set that looks like this, where P is my clock's skew relative to the master. It basically introduces this additional error term over here. Okay, so let's step back for a second and think about this equation. This equation basically tells you the maximum error that your clock could be wrong if you pick the midpoint to synchronize and use that offset to adjust your clock. Okay, so there's a couple of really interesting factors about this. One thing that it says is the rate at which my clock synchronization error grows is proportional to the round trip time, T2 minus T0. So the larger the round trip time, the worse off my maximum error ends up being. Another thing that it says is if my clock is proceeding at a higher rate than the master's clock, then that difference in rate, that skew, also is proportional to the maximum error. So the higher the skew between my clock rate and the clock's clock rate, the greater the bound on the error. And the last thing that it says is, if I happen to know the minimum round trip time, then I can subtract that off of this maximum error. And basically, instead of doing T0 and T2 as the maximum bound, I can adjust that inwards according to the minimum round trip time. Okay, so all of this being said, if I know the minimum round trip time between myself and the master, what's the best possible clock error that I can achieve?
0.
That's assuming that my clock skew is also 0.
Yes. If you're lucky and you get minimum transmission time to and back, and they're symmetrical, then it'll be 0.
I think that's right. So if your clock happens to have 0 skew, which it won't, and if you're lucky and your round trip time is also that minimum, then you can synchronize clocks precisely. Clock skews affect that. What's a realistic clock skew? 70 microseconds per second, so 0.000007. That times the round trip time is a minimum error that you end up having. That can be pretty small for small round trip times. But one of the things that you said is if you're lucky, you get that. Why do you have to be lucky?
Because you're not going to hit the minimum. You're going to hit most likely the mode in your transmission.
So this is exactly where your probabilistic comment comes in here. So what this basically says is if you know min, let's say that you do, you can tune the accuracy with which you do clock synchronization by throwing out samples for which the round trip time is too big. And you can basically pick what error that you want. The larger the error that you allow, the more likely you're to measure that round trip time below that error threshold. The smaller the error that you want, the less likely it is that you'll actually achieve that round trip time. So this basically gives you a probabilistic method where you measure a bunch of interactions with the server and toss out all the ones that you don't like because they're too high of a round trip time. And that basically reduces, it gives you a trade-off between the accuracy of your clock and the probability that you actually successfully achieve clock synchronization. That, in the end, is the right way to think about all of this. Yep.
Well, I'm not convinced it's the right way to think about this, because you're throwing away, basically you said, let's take the ones where the round trip is too big and we'll throw them away.
Yep.
But all of that's information. So you're throwing away information that you might be able to use, because a lot of this math is based on a sample.
Right.
Right? And I think there's probably a lot of statistical machinery that you could bring to bear if we could take lots of samples. And throwing them out may give you something efficient, but it's all got data. You might be able to do something with that.
But I think you're going to have to make additional lists. I think your intuition is right, but I think in order to take advantage of measurements that exceed that round trip time threshold, you're going to have to assume something about the asymmetry of propagation delays. So one of the base assumptions that we started off with on this set of calculations is you can't know alpha versus beta. If you can assume something about the probability of alpha versus beta, then I think you can milk out a little bit more information. But if you can't, if you can assume it can lie anywhere within that round trip time, then I don't think you actually get anything. I claim.
Could we also get a bit more accuracy if we do take into account the cable modem asynchronous transmission rates?
That's basically trying to milk something out of alpha versus beta.
Yeah.
I think you could, yeah. If you had some way of...
Like whenever you use Comcast, or whenever you're coming from a Comcast IP address, then do like a 1/3 or something.
Right, but now the trick is, what ratio do you set that to and how do you measure that without synchronized clocks? You can assume that latency is inversely proportional to bandwidth or something like that, and maybe that'll get you close. But again, you're starting to make some assumptions that might not be true about the actual network.
Well, and I think the behavior of cable modems as described may not have been really precise, because I think the signaling rate is the same up and down.
Right.
But the total bandwidth available is different. So up packets still may travel at the same speed. They may just delay some of them.
Right,
For the
exactly.
purpose of extorting you for a few more dollars a month.
And where that delay happens and how long those queues grow starts to impact all of this. I think that's right. Okay, enough about physical clock synchronization.
So one question is,
Yeah.
the master could also bounce a message from the slave, which can give you information about the relationship between alpha and beta.
Say more? I don't think I understand how it would do that.
Just like the client is pinging the server and getting back and doesn't really know precisely what's the ratio of alpha versus beta is.
Yeah.
Well, if a part of the protocol was for the server to send a message to the client and the client immediately returns back, and then the server can report back the information that is fine. There could be something out of that which you can estimate alpha and beta.
I claim not. I claim that either interaction, whether it's initiated by the client or initiated by the slave or initiated by the master, in either case they involve one trip in this direction and one trip in the opposite direction. And you have no way of distinguishing the relative latencies of those.
Could they both ping an intermediate host?
Oh, geez.
Oh, what if the master sent back 3 equally spaced packets? Or,
Still doesn't help you, I claim. So I don't think it helps you.
The intermediate host ping both of them.
Exactly. I don't think that helps you. Because again, you don't know the asymmetry between A and B or C and B. So it doesn't help you figure out the asymmetry between A and C.
But if you know the round trip time between the person in the middle and the one on the left versus the round trip time of the person in the middle and the one on the right, if they are apart, you will see that. The round trip time got larger.
I don't think I fully understand what you're suggesting, but I suspect that it assumes that the triangle inequality holds on the internet, which it doesn't. So, sadly, I think that paper's been written. Yeah, exactly. Okay.
It's just a freak. I mean, yeah, it doesn't actually work because 2 lines could be,
Yeah, exactly. Go ahead.
So actually, could you go back to the timing diagram that you had before?
Yeah, sure. Just let me bring it up.
Oh, not that. I meant the one that you had on the slide.
Yeah. This one?
Yeah, so I mean, hypothetically, suppose you had 2 observations, one in which T1 actually fell right after the transmission from the slave to the master would achieve the minimum latency in that direction.
So alpha equals 0.
Alpha equals 0, yeah. And then you had a subsequent observation where beta equals 0, and you knew that the skew was bounded by some amount. Then couldn't you, at that point, use a combination of those 2 observations to figure out? In one scenario, if you know that you fall very close to alpha equals 0, and in one observation you know that you fall very close to beta equals 0, then the combination of those 2 be better than either one in isolation.
I can't prove to you why yet, because I have to think about it a little bit more deeply. But my intuition is screaming, no, that doesn't give you any more information at all. That you can't tell the difference between having learned something about alpha versus beta versus being wrong about the degree of your clock offset. The first time you do a measurement, you have a certain maximum error bound of your clock offset. The second time you do the measurement, you similarly have a maximum error bound. The most that you can do is reduce that to the minimum of those 2 error bounds. It doesn't tell you anything about where within that bound the measurement of T1 actually lay.
Okay, let me think about it a minute.
Yeah, think about it a bit. But if you can prove the answer, if you can disprove me, there is a paper line there. But I don't think you can. My intuition is saying it doesn't actually buy you any more information. Let's start into logical clocks, and then we'll take a break partway through this paper. Okay, so let me start this paper by asking you how to build a motivating example service. So let's imagine that our goal was to build a distributed make. So basically a make file that's distributed. And the way that this is going to work is you have an FTP server that stores the source files, the object files, and the executable. And you have clients that can fetch a file from the server, compile it to produce the object file, and then store the object file back on the server. And the clients are the ones that set the timestamps for the files. Okay? So rather than the FTP server setting the timestamps when it receives the file, clients set the timestamp when they transmit the file. And the FTP respects that timestamp. So the goal is to build a parallel or distributed make where I can have multiple clients interacting with the FTP server simultaneously to figure out which files they ought to compile and which ones not. Okay? So basically the way the compile service works is in the worst case, you're going to recompile everything based off of the dependencies. But in the best case, if I notice that the object file timestamp is more recent than the source file's timestamp, then I can assume that the object file is correct with respect to that source file. On the other hand, if the object file's timestamp is less recent than the source file has changed since the object file was produced, I'm going to have to recompile that source file. Okay. So if I'm using client timestamps, I've got multiple client machines that are interacting with the FTP server. Does it work?
Not without the clients are synchronized.
If the clients are synchronized, how closely do they have to be synchronized? And why? Why do they have to be synchronized?
4.5 days back, then
they would never, even if it just compiled one, it would never be picked up by the other clients as being compiled. The server shouldn't accept client's timestamp.
Oh, the server should not accept client. Why not? So let's come back to you, because I think you're, before I come to you, let's finish off that thought. I think you're right. The worst case is a client modifies the source file. The client's clock is really, really stale, like really old. And therefore the source file gets transported back in time. And it looks like the object file is up to date, but it's actually not. Okay. So you're saying the server shouldn't accept client's timestamps. Why not?
Because it's kind of a causal dependency that the client gives it after finishing its task and the server is storing it. And other clients are going to use this timestamp to decide whether to take it or not.
So I think what you're saying is the problem is we've got multiple clocks if we're using client's clocks. And I think your implicit proposal here is to use the server's clock instead.
Yeah, and when the clients run the files to compile, they have to compare the timestamps of the object files against the timestamp served by the server, not against their own timestamp.
So basically, I will ask for the timestamp of the object file and the source file from the server, and compare those server-based timestamps. Okay, now let's modify the design a little bit and say my source tree is so big it doesn't fit on one server. Like, I'm going to win this argument. I can make it as complicated as we like. Okay, so you said it's a problem if the clocks aren't synchronized. So how tightly do they have to be synchronized for this to be okay?
As accurate as the timestamps themselves. If you're more synchronized than that, if you can't stuff the bits into the timestamp, that doesn't matter. Your timestamp's like, I modify the source file at a second resolution. It doesn't matter if your clock's synchronized to the millisecond. You simply can't say that to the file system.
Okay, so certainly your timestamps themselves have to have a lot of precision to them. Let's assume that we've got
100 nanoseconds on NT.
Say that again?
Windows NT gets 100 nanosecond timestamps on file types.
Okay, so let's assume that we've got Windows NT then with 100 nanosecond timestamps on files. Now how tightly do the clocks have to be synchronized on the clients for this compile service to work?
They just have to be within the amount of time it takes for the smallest object to be compiled.
Close. I think it's the smallest amount of time that it would take for that object file to be fetched, compiled, and stored.
Right.
So that's basically the bound on clock synchronization that we have to end up getting. So one way that we could build this distributed compile service is with physically synchronized clocks. The other way that we could do it is with logically synchronized clocks. Let's start walking down the path of what a logically synchronized clock actually means. But roughly, the intuition that I want you to have is the problem is if we don't have physically synchronized client clocks, then causality is no longer respected. That in order to have a correct make, we need to make sure that any changes to the source file propagate to changes to the object file. That if we don't have that sort of causal relationship, that we end up being in trouble. Said a different way, causality is at the core of this distributed make problem. Okay, let's talk about causal ordering a little bit. So in the Lamport paper, Lamport basically goes through 3 intellectual leaps in order to come up with a causal clock. And I want to walk through those step by step. The first leap is to figure out abstractly, without even thinking about clocks, what it means for events to happen before or after them, each other. The second leap is to, using that, figure out what the abstract requirements of a logical clock are. And the third leap is to then propose an implementation scheme for a logical clock that meets those abstract requirements. So let's walk through those step by step, and we'll take a break partway through. So here's the picture that Lamport draws. Time in this diagram flows up, physical time. We've got 3 processes. Each dot represents an event happening on that process. And you can see that there's basically 3 kinds of events. There's some local event that happens on that process. There's the sending of the message, and then there's the receipt of that message. And those are the three types of events that you can end up having. So let me start by asking this. What's a process? Said a different way, if I were to take some real physical system, how would I decide what the processes are in order to draw this diagram?
Sequence of ordered events.
Wow, I like that definition. Say more about that.
Well, a process can be broken down into several events, and every event, the state of the process changes. Start with that.
So is a operating system process something that can be drawn as a process on this diagram? No, why not?
Because it has multiple threads.
It could have multiple threads. And why is that a problem?
If they run on multiple processors, then they're running concurrently.
So there's some relationship between events happening concurrently and your definition of things have to happen sequentially. Can you help me pin down that relationship?
I'm pretty sure that if you have like an operating system running on a two-processor machine, you can just view it as two separate processes.
So you could treat each processor as a
Yeah.
separate process and look at the instructions happening on that processor as the events. And if I'm context switching between processes, then I'm sort of collapsing a whole bunch of processes events onto one event timeline.
Yeah.
That's one way that I could draw this picture.
You could also take any one process and view it as an arbitrary number of independent processes. That would be self-consistent.
Right.
You just cannot do the reverse.
Right.
So if you have a single core computer with hundreds of threads running on it, you can see each thread as a separate process.
Right. So trying to put my finger on it. From Lamport's point of view, all that matters is that I'm able to define a sequence of events, and no two of those events can happen concurrently. There actually has to be a well-defined, observable before and after relationship between any of those events. This means two threads within the same process running on separate processors doesn't have that property because instructions can be issuing at the same time, and it's hard to know which direction to order those relative instructions. Okay, could we do that? This is kind of a tangent, but could we take two threads running on separate processors and decide the order in which their instructions issued?
Sure. You would have to.
Who said sure? You
Yeah,
did.
you can decide. You can just make
Have-
an algorithm. Right? Doesn't mean they'll be right.
Oh, you could do that. You could just arbitrarily decide. Fair enough.
Prefer one.
Is there a
most of us
meaningful way?
program most of the time, as if that really was the way it worked.
You could do it. You could always do this process, then that process, for example.
Yeah.
Is there a meaningful way to do it? And by what criteria are you impugning meaning?
If the threads need to be communicating with one another like that, then you would have to come up with a scheme like that to
If the threads
lock
share
objects.
memory,
Yes, lock objects, synchronize on that, execute, go to the next block, etc.
well, this is starting to get really, really interesting. Okay, so if those two threads interact with each other through either locks or memory, that introduces causality relationships between those instructions and those threads. So we'd basically have to figure out what a message means in that particular point of view. And instead of all of those threads, and basically draw a box around those threads and collapse that down onto a single timeline in a way that respects that causal relationship. Okay, that's too complicated. Let's table that for a second and come back to it. Let's assume the really simple case that each one of these lines is just an individual thread in a program, and the threads only communicate with each other by sending messages to each other. In that case, we have the nice property that we can treat instructions or groups of instructions as individual events. We can order them in a fixed sequential relationship. Okay, so in that case, we basically have defined intrinsically what it means for one event to happen before or after another event within the same process. We've decided on that order, and that order defines the happens before relationship between those two events. Okay, if let's switch to the next thing, these wavy lines in the picture. So if one process sends a message and another process receives that message, in which order do those events happen?
Sending happen first.
Sending must happen before receiving. Why?
Otherwise it wouldn't
Because I
be
have to
received.
stand properly.
Sure, but why can't that be instantaneous? Let's start with that. Let's start with the more obvious one. Why can't I send after you receive?
It requires, the message requires a certain fixed time to travel.
Let's come back to that. So you're claiming a message has a non-zero propagation delay and a must. That's a different way of saying that the receive must happen after the send. But let's ask the dumb question first and then the harder question second.
Conservation of matter.
Say that again?
Conservation of matter.
Conservation of matter? Where did that come from?
So if you receive before I send, it means that the matter is in both places.
I think it means I've got a time machine.
Yeah.
Which we don't know how to build yet. So causality says sends and receives have to happen in a certain order. And it's not meaningful for a send to happen after a receive. Because how do I anticipate what message you're going to send if you haven't sent it yet? So the arrow of time must move forward. Why can't a send and a receive happen at the same time? Let's say our two processes now are actually threads inside of one address space. And the message is done by reading and writing from shared memory locations.
Aren't they trying to get this to work with quantum computing?
That's a different thing they're trying to get to work, which is all possible states of the system to coexist at the same time. But I don't think that buys them.
Effect happens happens remotely. I think.
That's spooky action at a distance, which is something else that people are trying to do.
Did they do that? Does it actually work?
I don't think so. I hope not. If it does work, then yeah. Okay, but let's come back to this example. Two threads, same address space. They share a memory, and I communicate with you by writing to a memory location, and you read from that memory location.
So the reader has to wait until the writer writes.
Serialized access to memory.
Serialized access to memory. The reader has to wait until the write is finished. The actual act of writing to memory takes a certain amount of time, because under the covers there actually is signal propagating through wires between the processor and memory. So even in that case, even though programmers logically think of memory writes as being instantaneous, they're not. They take a certain amount of time, and you can't read my write for some amount of time until after my write is finished. So even in that case, there's a fixed propagation delay inside of memory. Okay, so far we have, within our process, if P1 comes before P2, then Lamport's happens before relationship says P1 happens before P2. Across processes, we have if P1 sends a message and Q2 receives that message, then P1 happens before Q2. Okay, so those are the two basic building blocks. And then we can transitively pump them in order to figure out the full happens before relationship. So this basically says, transitively, if A happens before B and B happens before C, then A happens before C. Why is that true? Again, really obvious question. Lamport kind of asserts it as being true without saying why it must be true.
So because the propagation,
Sorry, one at a time. Go ahead.
Propagation delays of there are two messages involved here, and so propagation delays of both messages add up. So there is a delay on transmission of message 1,
right,
and there is a delay on transmission of message 2. So cumulatively, both add up to say that okay, A happened before C.
But basically, the arrow of time is moving forward for both of those hops. Therefore, it moves forward for the entire transitive hop. Okay. So graphically, how does the happens before relationship manifest on this picture? If I wanted to point to two of these dots on the picture and ask you whether there's a happens before relationship, how would you test to see whether or not there is?
There was a line between them.
I believe there's a message between.
Okay, so if there is a line between them, if, for instance, here's Q5 and here's P4, there's a line between them, therefore Q5 happens before P4. Similarly, P3 happens between P4 because there's a line between them. how would you decide whether or not Q2 happens before P4?
Well, you can use this model.
It's a directed graph. If you can find
If
a
you
walk, you're good.
If you can find a walk, say more about that.
It's a directed graph. So
Yep.
if you can find a walk from one node to the other,
If you can follow these process lines up and these message lines over
Yeah.
and find a path between two dots, then there's a happens before relationship between them. So let's stare at this a little bit more. Does P1 happen before Q1?
No.
Not necessarily.
Can't say.
Can't say, no, not necessarily. So, can't say. Why can't you say?
Because both of them have independent counters, kind of a thing. Like, we really
We haven't
don't
even talked about counters
Okay.
yet. So just in terms of causality and things happening before
There's
each
no
other.
dependence on Q1 and Q1, and so you cannot really, you don't have to define a happens before between those two processes.
Using the happens before relationship that we've defined so far, there's no way to find a path between those two events. I think that's what you're saying. Go ahead. Did you have something?
Oh, assuming that this is the total state of the system, there could be
Ooh, say more about that. I like that thought.
there could be a fourth process we could add to the system with,
Oh, I see.
with lines that could force.
So if this is a complete set of processes, then we can't say that there's a happens before relationship between them. There's a mysterious fourth process that receives a message from Q and sends it to P, and then there might be an ordering between these events. So one thing that we have to assume is that there are no other processes in the system. Similarly, we have to assume that all communication channels are reflected by wavy lines here. That there's no hidden communication channel that's not reflected inside of the system. So if we make those two assumptions, there are no other processes and no other communication channels, is there a happens before relationship between P1 and Q1?
No.
So can we say that they happen concurrently?
They might.
So you're shaking your head yes. So why can we say that?
By the definition in the paper, you can say they happen concurrently because there's no happen before.
So I think that's right. So implicitly, you're defining concurrent.
Okay.
What are you defining it to be?
If there is no relationship between the two events, they happen concurrently.
If there's no causal relationship, according to Lamport's happens before to relationship, then causally they're concurrent.
Correct.
Are they concurrent in time?
They don't have to be.
No, they might not be. There might be an actual well-defined order between them. And if we had physically synchronized clocks, we might be able to measure that. So given that there might be a physical ordering in time, why is it still correct to think about these things as being logically concurrent?
They do not causally affect each other, then it really doesn't matter what order you put them in.
Yeah.
It doesn't matter.
I love that.
Lampart would appeal to special relativity and say the ordering would be dependent upon the observer.
Lamport would say it's a mystery of the universe that we could have physically synchronized clocks to capture all independencies, I think. But I want to come back to what you said, so hold on to that. Say what you said again.
Can you say what I said again?
I think what you said is
there's no
because
causal relationship.
there's no causal relationship between the two, P1 and Q1 could not have influenced each other.
We also have transitivity. That's also important.
And P1 and Q1 could not have been influenced indirectly through other processes either. Therefore, there is no influence between these two events. There's no cause and effect. Therefore, we might as well think of them as happening at the same time because, and this is the really deep part of it, nobody in the system can prove otherwise. Right? From the point of view of any observer in the system, either order is possible, assuming we don't have perfectly synchronized clocks.
Aren't you saying if it doesn't matter, we don't care?
If it doesn't matter and we don't care. Yeah.
If it doesn't matter. So if the causal relationship isn't important for the actual running of the system, then we don't care about which one comes first.
I want to be precise about this,
Well, I mean-
be a little pedantic. But I think what let me try rephrasing it and see if you're happy. if there's no causal relationship between the events, then it doesn't matter which order we assume them to have happened in.
But
Either one
but
is.
the reverse is not true. Just because I don't care about the causal relationship doesn't take that away. The fact that there is I might not care that Q2 actually follows P1 in the diagram, but Q2 does follow P1.
How do you know?
Well, there's a message between them.
There isn't.
In this case, between Q2 and P1.
Oh, between Q2 and P1.
I might not care that Q2 happens later. Yeah.
So one thing that you're saying is,
Maybe
if there is a causal relationship between two events, that might introduce some constraints in the system, and it might not. It depends on the nature of that causal relationship.
And just because there are no observable constraints doesn't change the fact that there isn't a causal relationship.
Oh, hold on. That I don't think I agree with. I think what you just said, let me make sure I got what you
Constraints is a
said.
prerequisite of having a causal.
I think what you said is, if there is no, say what you said again.
If there is no state change on process Q as a result of receiving the message from P1.
If the receipt, I think what you're saying is, if the receipt of P1 has no side effects, then what?
Then I'm saying it's still important that Q2 is after P1, that P1 caused Q2.
Why?
Is it not?
If there's no side, this is a really deep question.
Yeah, it's like if a tree fell in the forest and nobody heard it, had it really happened, that's
If
kind of what it is.
P1 shows up, if the message from P1 shows up at Q2, and Q2 drops it on the floor, there are no side effects inside of process Q of receiving that message, then it's as though that message was never received.
Okay.
And therefore it's as though that message was never sent.
Is that actually true? What if you needed to prove that P1 happened before something else that resulted in the communication between P1 and Q2? Like, say there was no state change between P1 and Q2, but after Q4 sent that message to R3, and you wanted to prove that P1 happened before R3, regardless whether Q2 dropped it on the floor or not.
But here's the thing. I love this discussion, okay? Here's the way that I like to think about it. These happens before relationships, really what they're trying to model is A happens before B means A might have influenced B. That A might have had some cause that takes effect on B. If we can prove that A had no influence on B, then it doesn't matter if A happened before B.
I guess what I'm asserting is that Q2 dropping the message on the floor is an effect.
Not from the point of view of Q.
I don't know. It depends, I would think.
Well, how?
I don't know. I'm just saying that dropping the message on the floor is an action, is a result of getting a message, right?
But does it actually affect the evolution of Q's computation? If the answer is no, then there was no side effect. If the answer is yes, then there was a side effect. I know it sounds
always
like
a side effect from receiving a message.
Like it's eating up DMA channel bandwidth or something.
Which could perturb some other timing, which would then have an
Anything else,
effect.
it just shifts like other events forward in time because it's there, right? It's occupying some time.
So really what we're saying is, from my point of view, I'm arguing that if Q2 has, the receipt of the message has no side effect, then something. And what you're telling me is, wow, you better be incredibly careful about has no side effect. That even timing effects can be enough for a side effect that changes the evolution of things, if other messages are arriving and the order in which they arrive is perturbed. So
it all depends on your abstraction layer, obviously. Q is a web server and P is the client, and you're only looking at HTTP messages. Yeah, there might be some broadcasts coming from R that changes your state, but you will ignore that for those two well-defined processes.
I think that's right. Okay, let me summarize and then let's take a 5-minute break, a shorter one this time. So what we've done is now figure out in the abstract what happens before means logically. And what it means is there's a causal relationship, or rather, potential causality. that if A happens before B, what we're saying is A might have influenced B. And that's a transitive property. So let's take a break there and pick up from that. Okay, why don't we spin back up? So where we left off was happens before relationship. We decided what A happens before B basically means is A might have influenced B. And we decided that A is concurrent with B basically means neither A influenced B nor B influenced A. Okay, so that's basically what concurrency means is there is no happens before relationship, and therefore these two events could not have influenced each other. So the next step that Lamport does is say, okay, rather than having physically synchronized clocks, let's see if we can build an abstract clock that respects this notion of causality and happens before. And basically what this means is we want each process to have a local counter. That counter advances over time according to some logical clock rate. So it doesn't have to have any relationship to physical time whatsoever. It's basically just ticking off events and maintaining a counter of how many events might have happened. But what we want is we want to synchronize these counters across processes so that any one of these counters is correctly interpreted as some global synchronized clock time. So said a different way, each process should be able to use its local counter in order to affix a logical timestamp to an event. If you were to compare those logical timestamps across processes, then we should have some sort of ordering relationship between those timestamps that's respected by causality. And Lamport basically pinpoints exactly what condition you need in order for this to be true. And he calls it the clock condition. So basically we have two events such that A happens before B, then we want the abstract clock reading for event A to be less than the abstract clock reading for B. So we should just be able to compare logical timestamps, and if A happens before B, we can be ensured that the logical clock of A is less than the logical clock of B. Okay, so that's basically what we're trying to build. Let me quickly do a pop quiz. Is the converse necessarily the case? If clock value A is less than clock value of B, is it the case that A happened before B?
If they're on the same process, concurrent.
If they're on the same process and we implement our clocks correctly, then yes. If they're on different processes, no. So just because there's a relationship in logical clock time doesn't mean that there's a causal relationship. But if there is a causal relationship, then we will have a relationship in logical clock time. Okay. So given that clock condition, Lamport basically boils it down to two subconditions. That basically is what we were just talking about. If we just focus on a single process, and we have two events on that process, such that A happens before B, then the clock counter on that process at A must be less than the clock counter on that process at B. Okay, so that's that first thing. The slightly more subtle one is this next relationship, which is if I have got A being process I sends a message, B is process J receives that message, then the clock at I of A has to be less than the clock at J of B. So said a different way, even though these processes have independent counters that are advancing, there has to be some relationship between them so that second condition ends up being true. Does that make sense? So that's what we're trying to build. Conceptually, here's the way to think about that. Here's that same picture. And basically what we have to do is end up, to synchronize these clocks, it's basically drawing a dotted line between these clock counters. So what we basically have to do, thinking about this as two steps, if we just focus on process B, here's one event, P1, and here's another event, P2. Since P1 happens before P2, the clock at P2 has to be bigger than the clock at P1. What that basically means is, given any two events that happen on a particular process timeline, the clock has to tick at least once in between them. So we have to draw a dotted line starting here in between each pair of dots on that process. In this particular diagram, Lamport showed two clock ticks happening. Why is that okay?
2 is at least 1.
2 is at least 1, so why does that make it okay?
Because there had to be at least one.
There had to be at least one clock tick, but why is it okay to have more than one?
It's increasing.
It just has to be increasing for this relationship to hold. So it doesn't matter how much it increases, it just has to increase some amount. So one of the things that this says right away is there could be a whole bunch of different ways to implement these logical clocks. There's not one prescribed algorithm. Right off the bat here we have the degree of freedom where the clock rate, the logical clock rate, you have to have some freedom in deciding what that is. We could advance the clock by 1 between each logical event on the same timeline. That's the simplest case. We could advance it by as much as we like, as long as we advance it. Okay? The second thing that it says is if P1 sends a message to Q2, then that wavy line has to cross at least one clock tick. Why?
Must happen after.
Q2 must happen after P1. Therefore, this abstract logical clock has to advance in between the sending and the receiving for that clock condition to hold true. So when we combine those two, you end up with a picture that looks kind of like this. And just like beforehand, we have the freedom to have as many clock ticks as we like between the send and the receive, as long as there's at least one of them. So when we put all this together, you basically end up with something that looks like that. And when you straighten it out, you end up with this picture, where basically this is one moment in this global abstract logical clock. So the local logical clocks would logically read the same at these values. They'd all tick like that, and they'd all tick like this, and so on. Okay, so that's what the abstract logical clock is. Yeah.
Is it true that P3 can be on any of those ticks between P2 and P4?
Yes. Why?
Causality. There's causality messages going in and out.
Nothing from Q and R restricts P3 from moving up and down. So the sending and receiving of a message, you can kind of think of this as being a causal constraint that boxes in some other events. And how much is this event boxed in? Well, it's boxed in by P2 below it and P4 above it, and by no message received whatsoever. So it's free to logically move up and down that timeline. Kind of the way that I think about this is the physical analogy would be these are beads on a string, and you can slide these beads up and down as much as you like. They just can't jump over each other. And any connections between the beads have to have a slope of at least 1.
Right.
Okay. But any manipulation of the beads is completely fair, and that's a clock that's consistent with Lamport's clock condition, and therefore is consistent with cause and effect.
Defines topology.
Yeah, if
You
I
can
were
warp it however you like, but you can't reorder things.
Exactly. If I was a mathematician, I'd tell you whether or not this actually was a topological property or not, but I'm not that good. So, okay, so that's kind of the requirements on an abstract clock. The next thing that Lamport does is he proposes an implementation of a logical clock. And here's what he basically says. What we're going to do is have 2 implementation rules. And if you follow those implementation rules, you've defined a logical clock that meets that abstract clock condition. Every process has a local counter. All counters start off, let's say, at 0. If I'm a process and I experience a local event, I increment my counter by 1. Okay? If I'm a process and I send you a message and you receive that message, what do we have to do?
Send your timer.
I have to embed inside of that message my clock's value. Why? What's the intuition behind why I have to do this?
Because you have to advance you have to make sure that receiving the message happened after I sent it. So you have to advance your clock if you...
The receiver has to advance it.
The receiver basically has to make sure that the receiver's clock is later than the sender's clock at the send time. So to do that, it has to have some measurement of the sender's clock at the send time, which means the sender has to embed its logical clock in all of its messages. So that embedding of that counter in the message is logical clock synchronization. Right? That's the process that's going on over here. So exactly the rule is when I send a message, I embed my local counter inside of that message. When you receive that message, you compare your local clock to what was inside of that message and pick 1 plus the maximum, roughly. I didn't quite say that perfectly. Why am I comparing my local clock to what's in the message?
Local clock would be higher.
How could that possibly happen?
Because you're going with different numbers.
Say that again?
You're going with different numbers. You're incrementing number. It doesn't mean you put the instance together.
Right. If you and I have not communicated at all, our clocks, local clocks, could be arbitrarily different. So if you send a message to me, my clock might have already been far enough ahead of yours that my clock is after your send clock. So the only time that I have to adjust it is if your send, local send timestamp is later than my receive timestamp. Then I have to adjust my receive timestamp upwards to keep these clocks in sync with respect to causality.
You also have to adjust your clocks at the receive, even if their clock is smaller, because you need that to be its own event.
Right. So the receiving of a message is an event unto itself. So once I've done this comparison and maximum, then I have to increment it by 1 again in order to compensate for the fact that the receiving was an actual event between other events on the same process timeline. Exactly right. Okay.
If you receive duplicate message, you still have to increment.
No such thing as a duplicate message in this model. Think about that. We never talked about the semantics of message send and receive reliability and ordering and all of those sorts of things.
Everything is unique.
Exactly.
But if the process is really long, we will run out of number at one point.
These are infinitely wide counters.
Nice.
If not, we're in trouble. 128 bits is probably fine, as long as you're incrementing by 1, not by a very large number. But you're right, if these are finite timestamps, eventually time will roll over, and then we're in big trouble.
We're not sure that doesn't happen.
It will happen in 2036 for NGP, or whatever that time is. Okay, so here's a proposed implementation of a logical clock. We can basically show that these two implementation conditions meet these two clock conditions, and therefore this implementation of the logical clock has this property that if A happened before B, then clock timestamp of A is less than clock timestamp of B, which is great. Is the converse true? No. Somebody point out to me a case over here where it's not true. Where the timestamp of an event B is larger than the timestamp of A, but there's no happens before relationship.
Q3, P3.
Yeah, Q3 and P3. So over here, Q3's clock timestamp is larger than P3's. There's a tick between them, but there's no causal relationship between them. So causally, they're concurrent. But in terms of logical time, one happened after another. Is that a problem?
Well, yeah, because if we are trying to order the events, theoretically, like P3 might have higher timestamp than Q3, and then even though it occurred like in the global time, in the real time, it occurred before Q3, it would still have a larger timestamp, and it would not be possible to order correctly.
Is that a problem?
But is that a problem, right?
Well,
So-
if it is, send a message, and that'll fix that.
So we could be constantly sending each other messages in order to induce causal relationships with doing everything. That causes all sorts of other problems.
If you needed that property, then I don't know what else you'd do.
But coming back to, I agree, but coming back to what you said, if you prefix that by saying the whole reason for doing this is to try to order events. So in particular, if these are writes to a shared database, then we want to respect the order of causality in that order of writes. Okay. So what this is basically saying is even though P3 and Q3 causally are concurrent, this particular system of clocks introduces an ordering constraint that's unnecessary. This particular system of clocks says Q3 happened later than P3. Therefore, you have no way of knowing whether or not P3 influenced Q3 just by looking at the clock timestamp. If you're using this clock to determine a global ordering, that global ordering will introduce constraints that aren't necessarily causal constraints, is a way of thinking about this. So this particular clock doesn't tell you whether or not two events were causally concurrent or not. If they are causally concurrent, those writes could happen in either order, and that's okay. But just by looking at the clock timestamps, you can't tell whether or not they're concurrent. So the clocks are introducing, they're sort of over-constraining the problem, is a way of thinking about it. Okay, so let's wrap up this with a harder question. So this is the property that we just came up with. With Lamport clocks, if A happens before B, then the clocks have that relationship if the converse isn't true. Can we implement a logical clock for which it is true? This is a deep question. Can you come up with a system of clocks or an implementation by which you can look at two clock timestamps and say, I can't decide if this timestamp is less than that one or not. Therefore, these events are synchronized. Say that again?
You gave me information synchronized, so I can.
You have to synchronize them somehow in order to respect causality.
So what you're asking is that CA and C, looking at them, you will know that they're concurrent.
Yes.
Yeah, I can build it, but I need infinitely many. I need a counter that's infinitely wide.
Why infinitely wide?
If we just let every event be a prime and the clocks be the product of them, then I can tell if it was before because I've got because the factor's in my number.
I don't think I understand that.
Every event in the system we're going to give a prime number to, and so we will increment the clocks by multiplying them.
But I still don't think this.
And so you know if some event in the past happened to cause you, his factor is in the number.
I don't think that gives you the proper. I think that still introduces relationships between the clocks where they don't need to exist.
If the two weren't causal, then the timestamp you're looking at will not have the factor of that event in it.
Still causality within the process.
Exactly. So if event B happened after event A within the same process, you're still doing that multiplication.
And that gets fed up to the next message.
Right.
Besides, you have
Yes, but you've still got that causal.
But every number can be compared to any other number.
No, we're not comparing by looking at greater than. You've got
something to say.
division.
Yeah, I think I have better idea. I think vector clocks will solve it.
Vector clocks. Interesting. Say more.
So vector clocks, like, it maintains its perception of the logical time progression on every other process. So if there is a concurrent event, then I will not increment that guy's logical clock for the timestamp of that event in my process. But it will get, so I'll have a view of my view of this time during my concurrent process.
Yep.
So I'll be able to order it because his would be different.
Yep. So, yes. Let's see if I can explain vector clocks. So before, with the implementation that we were talking about, every process maintains a single counter, which is its local clock. With a vector clock, every process maintains one counter per process in the system. Okay? So I basically have a vector of timestamps at every process. Now the implementation rule is this. If I've got two events within the same process, I implement my counter, but not other people's local counter copies. If I send a message to you, I copy my entire vector into that message. Then you compare every element of my vector with every element of your vector and increment the ones that are less than. So it's basically a way of me estimating not only what time I think it is, but what time I think you think it is. And I carry that whole information through. I didn't say that very, very clearly, but I'm going to let you read these slides offline. Basically, I changed the implementation rules so that when you send me a message, that message contains a vector timestamp, and I'm doing individual comparisons on the components of that vector, advancing potentially multiple local clocks as a result. What this basically does is guarantee that if two events are concurrent, then if I take a look at the timestamp of those events, one clock won't strictly dominate another one. That some component of that vector clock will be less and other components will be greater than. So I can actually look at this and in some cases decide that this clock strictly dominates that clock, in which case there is a causal relationship between them. But if those clocks don't strictly dominate, then there isn't. I'm going to leave that kind of hanging there. But it's basically a way of, through additional state and more computation, precisely tracking causality through this distributed system and ending up with timestamps that don't strictly dominate each other in the case of concurrent events. So this is one of the beautiful results where if I choose to have a little bit more overhead, I can build a logical clock that precisely tells me whether or not A happened before B or whether A is logically concurrent with B. Lamport's paper doesn't go that far. Lamport's paper just does half of that relationship. But it turns out that you can do the full, both directions of this and track causality that way.
Extend this even to a matrix.
Say that again?
You could extend this even to a matrix, from a vector to a matrix.
And what would the matrix clock buy you?
So a cell Jk maintained by a process Pi would mean that J's perception of the logical time of K. Pi's maintenance of J's perception of the logical time of K.
What does that bring?
Yeah, what property does that buy you that a plain vector clock doesn't already give you?
It's beautiful math. Let's not turn it off with physics.
Think about that. There might be some property that it buys you, but I think vector clocks already give you the full logical causality tracking. Okay. All right, mental floss for a second, and let's get to one more beautiful result of distributed systems, which is global snapshots. And let's start this off by asking this hypothetical question. Let's imagine that I've got a parallel computation. So I've got a bunch of computers. I'm doing particle simulation in parallel across those computers. So one computer is periodically exchanging, here's where all of my particles are, to that computer over there. And they're computing the forces between that periodically in order to do this in parallel evolution of the entire system. Okay? So I basically have a parallel computation that's exchanging messages between the computers in order to bring each other up to date. Here's the bad news. If one of those computers crashes, the entire computation is going to halt. Okay? And if that computer that's crashed, if I haven't saved its local state, then I've got no choice but to restart the entire computation. Right? So if I have this parallel computation, if I'm not snapshotting the local state of each computer, I'm in potential trouble. If any computer crashes, the entire computation fails. So one of the things that I might want to do is periodically snapshot the states of individual computers so that I can resume them post-snapshot. For this to work, how often do I have to be snapshotting individual computers? You're all tired, I can tell.
I'll just say it was 3 minutes.
Let's say that I do that, and a minute after my last save, my computer crashes. What do I do?
You roll back to the last snapshot.
And is that
Across
okay?
the whole, you need to roll back across all the nodes.
Oh, so every computer snapshots every 3 minutes. And how close in time to each other do those snapshots have to be?
Very,
What?
very close.
How close?
Less than a shake.
There was a comment from Microsoft. What was that?
That'd be a logically concurrent.
Oh, that was deep. Logically concurrent with respect to each other. Why?
So that way you can be sure that you're not you don't restore one computer to a state that would affect some other computers, like future state, which it'll affect it in a different way that it wouldn't have before.
So roughly those snapshots have to be causally concurrent with each other if you're going to dump and restore from all of the snapshots simultaneously. Otherwise, there's some causal relationship that's embedded in the snapshots. One snapshot will reflect a message received, but another one might not have sent the message. So roughly what we're trying to do is coordinate these checkpoints to follow the rules of causality. Okay, see what I did there? I tied that one paper to the other paper.
Nice.
Okay, here's a way to think about this. For whatever reason, when we're doing global snapshots, time goes to the right rather than up. I've never understood why. But here's the same kind of a system with 3 processes. In this particular system, these diamonds are checkpoints. Okay? So this is where a local checkpoint has been taken. So in the system on the left, what I claim is this is not a globally consistent, this is a globally consistent state. If we take a look at these individual messages, P2 doesn't reflect the receive of any message. P1 doesn't reflect the receive of any message, and nor does P0. P0 reflects the send of the message, and maybe that will show up sometime later. On the system on the right, I claim that this is inconsistent. If you take a look at P2, P2's checkpoint reflects the receipt of a message, but P1's checkpoint doesn't reflect the send of that message. So if we were to roll back to that contour through all the checkpoints, we'd be in trouble, because one process has received a message that another process has not yet sent. Yep.
So this is assuming that P0 knows that it sent M1, but it hasn't been received yet?
Why do you need to assume that?
Well, I'm sorry, on the consistent state.
So here we can decide one of two things. We can decide that we're going to switch to a system model where message delivery is unreliable, in which case restorative to this checkpoint is okay, even though that message will never be received. It's as though that message was lost on the wire.
Doesn't that mess with causality?
For a message to influence a receiver, it has to be received by the receiver. So I don't think it messes with causality. From the point of view of P1, message 1 will never show up, but that's okay. It's just as though that message was dropped on the wire. That's one model. Another model is one where we decide that messages are reliably transmitted, in which case we not only have to checkpoint these processes state, we have to checkpoint message is in transit channel state. Yeah. So in that model, not only would I have to have checkpoints here, any arrow that crosses that contour is a message that's in transit that's not yet been received that needs to be saved inside of channel state. Yeah.
And when you restore, you have to resend it.
You'd have to resend it or re-receive it, or yeah, exactly.
Is that the formal model that's presented in the paper?
In the paper, the model is reliable in-order message delivery. Yeah. So
the snapshot contains the pending message of the channel.
The snapshot not only contains the process's local state, it contains any messages that are in transit that flow through that cut. Yeah. And to get back to the point of Microsoft, this cut is basically causally concurrent states. Okay. So let's take another point of view of this. Let's think about I stole these slides from somebody else, you can probably tell. Let's take a look at this more complicated example. So here we've just got 2 processes. We've got a series of events on them, local events and message sends and receives. And what I'm going to do is draw a series of cuts, a series of sort of coordinated checkpoints. And we're going to think about how these series of coordinated checkpoints reflects the evolution of the system. This will become clear in a second. We'll start with the easy case, which is imagine that we gathered checkpoints at the very beginning of those 2 processes' execution. Is this consistent? Why?
Nothing has happened.
Nothing has happened. Every message that was sent is reflected in the receiver state because no messages were sent. Okay? So we never violate causality.
I just want to ask a nomenclature question. Where is it legal to draw lines? Between dots or on dots? Or?
Between dots.
Between dots, okay.
Yeah. So I'm going to name this state
Start.
E00. The first 0 means that P1 is at state 0. The second 0 means P2 is at state 0. So that's what this E00 is reflecting. So now let's imagine that we advance the system one event. So now P1 grabs a checkpoint here. P2 grabs a checkpoint there. Okay? Is this a legal, globally consistent snapshot?
Yes. Yes.
Why? It's concurrent. Any message that is received in a checkpoint, the sender is also in the sender's checkpoint because no messages have been sent yet. The way to think about this is this global state E00 has evolved into global state E10. Here that 1 means we did a checkpoint after P1's event number 1. Alternatively, the system could have evolved a different way, and we could have instead grabbed that checkpoint. Okay? Is this a globally consistent snapshot?
Yes.
Okay. So which of E10 and E01 actually happened in the real system? There's these 2 snapshots that we've gathered. They reflect different evolutions of the system. Which one actually happened?
No way to tell.
Either one.
Either one could have. From the point of view of any participant in the system, they can't prove or disprove either one of these. Either one of these evolutions could have happened. So this is 2 feasible paths the system could have evolved. Let's continue down this thought process. Here's the next one. I could have gotten there one of 2 ways, either from E10 or from E01. Both of those are possible. Is this a consistent snapshot? Why?
All messages.
The only time it's inconsistent is if you received a message that wasn't sent.
Right. The only way that this could be inconsistent is if somebody's checkpoint reflects the receipt of a message, but the sender's checkpoint doesn't reflect the sending of the message. So here, that message in transit is either dropped on the floor or it's captured in the channel state, depending on which of the 2 models we're talking about here. Okay. How about this one? Is this a legal snapshot?
No.
Why not?
P1 received what P2 was received in the past.
Exactly. It was this snapshot shows a message being received, but doesn't show the message being sent. So this global snapshot violates causal relationships, which means I'm not going to draw this on this lattice of execution states. It's not a feasible execution path for the system to go down. If I grab that snapshot, it would be a busted snapshot from the point of view of causality. How about this one? This one's okay for the same reason. How about that one? It's okay for the same reason. If we keep drawing this, we keep seeing more and more evolutions of the system as we try out all these different possibilities. And in fact, we end up with something that looks like that if we go all the way to the end of it. Okay, so here's some intuition that I'm trying to convey on this. Notice that this isn't a perfectly symmetric lattice. Some parts of this have been chomped out. Why?
Those parts contain the
They contain invalid states.
and those states generate.
So the things that have been knocked out of this lattice are invalid states that couldn't possibly have existed inside of the real system. And what events in the actual system cause things to be chomped out? Receipts of messages, exactly. So the receipt of a message is a causal event that constrains what execution paths might have actually happened inside of the system. Every time you receive a message from another computer, you're factoring out a bunch of execution states that now no longer make any sense. You've introduced a causal constraint between 2 execution paths inside of the system. And that causal constraint gets reflected in sort of chomping out these states inside of this lattice. Okay. So let's circle back to Lamport and Chandy's paper on this. So what Lamport and Chandy basically say is one of the reasons that we care about these snapshots is to test whether a stable property of the system has happened. Like deadlock is a stable property. The way to think about this is basically, if we take a look at these execution runs inside of a system, if deadlock happens in one of these particular lattice states, then everything that flows from that will contain that deadlock as well. Okay? If one of these lattice states doesn't contain deadlock, then everything that flows into it doesn't contain deadlock. The stable property of the system, once it fixes itself, it's like taint that flows through this execution downstream. Everything upstream of it is not deadlocked. Everything downstream of it is deadlocked. Okay? So the way you think about snapshot algorithm is that snapshot algorithm starts at a particular moment in time in one of these execution states of the system. That snapshot algorithm takes a certain amount of steps to complete, and that snapshot algorithm will eventually terminate when the system's in one of these states. Okay? So if my snapshot starts in, let's say, E22, and my snapshot finishes at E55, what are the possible states that are reflected in the snapshot? Which of these lattice states might that snapshot end up reflecting?
Anything that's going down from E.
Number of possible paths.
Anything on the path between E22 and E55 could be a conceivable snapshot of the system. That's the way to think about what the snapshot algorithm is doing. The actual system will flow down one of these paths. The snapshot might be on a completely different path. So it could be that my global snapshot's a state of the system that never actually happened. Why is that okay?
Because it could have happened.
According to whom?
According to the causality between the processes.
According to causality and according to any individual observer of the system, it can't prove or disprove that that state didn't happen. Okay. So now to circle back to that invariant. If a snapshot contains the fact that the system is deadlocked, then is the system deadlocked when the snapshot finished?
Yes.
Exactly. So if I gather a snapshot and I test those checkpoints to see whether or not they reflect a deadlock, if they do, I don't care whether or not that snapshot actually occurred or not, because that deadlock is a stable property. It's going to flow throughout this entire lattice and contaminate the end of the snapshot algorithm. Does that make sense? Yeah.
So what you're saying is, for example, the deadlock could be in state 4.3, which, let's say your system actually passed through 4.3, but the snapshot did not pass through and took.
Let's say this path.
Yeah.
And snapshotted E34.
Yeah.
So in that case, the snapshot won't reflect the deadlock.
Right.
Does that mean the deadlock didn't happen? This means that you can't prove that the snapshot, it might have been the case that the snapshot was taken before the deadlock happened.
Right.
In this case, I believe we know the deadlock will happen. Omnisciently, the snapshot has not.
So then if we were to start another snapshot, in that case, that next snapshot, since it starts with the system in a deadlocked state, that snapshot will reflect the deadlocked state, because everything downstream is tainted with deadlock.
Suppose that we can take a snapshot while it's deadlocked.
Let me say it a different way. So there's 3 moments in time that we might be thinking about. At some moment in time, the system decides to begin a snapshot. At some moment in time, that snapshot finishes. If I were then to look at the snapshot, it reflects some moment in time in between those points. If my snapshot reflects deadlock, then I know the endpoint is deadlocked as well. If my snapshot doesn't reflect deadlock, then I know the starting point wasn't deadlocked. That's all I can say about these snapshots. So if a deadlock happened in physical time concurrently with the snapshot, then I know that the endpoint is deadlocked. And therefore, if I were to begin another snapshot, it would definitely reflect that deadlock. I think that's what you're saying.
What is the use
if you're deadlocked in presumably the system can't do any computation whatsoever, including taking a snapshot.
Oh, but let's say the database is deadlocked, but the messaging system is still functioning.
Then that makes sense, yeah.
Yeah.
I'm not getting the useful property there by explaining that. What is the inference you're making by?
The inference is this. I'm going to gather one of these global snapshots according to Lampport's algorithm. I'm going to examine it to test whether or not I can observe a deadlock. If I can, I know the system is permanently deadlocked. Even though that snapshot doesn't necessarily reflect the state the system went through. If the snapshot reflects deadlock, then I know the endpoint of the system is deadlocked as well. So if a snapshot reflects some stable property, then I know the system has that stable property by the time it reached the end of the snapshot. And that's the important property. Okay. Go ahead.
What do you mean by a stable property? So that you're not talking about something that is just changing state on one of the processes.
No, a stable property is something that basically means if this invariant is true, or this condition is true right now, it will be true forever. Like, this is a token ring and the token has been lost. Or this is a series of locks that are being grabbed by multiple processes, and there's a cycle in the locked graph, and therefore there's a deadlock. So these are properties that once they're true, no matter how the system continues to evolve, they'll forever be true. Okay.
But it could be a deadlock in one of those states, those possible states that will not be reflected in the snapshot.
That's right. It could be that a deadlock occurred in between the snapshot starting and finishing, but my snapshot doesn't reflect it.
But a later snapshot.
We'll definitely do that. Yeah, exactly right. Okay. I think we're running low on steam, but let me ask a couple of questions. I wanted to briefly go over the Lamport algorithm itself, but before I do that, I want to talk about some alternatives. So remember that what we're trying to do is gather a series of local snapshots plus channel states and somehow coordinate them so that causality is respected inside of those snapshots. Here's one alternative algorithm. There's a snapshotter process. It tells every other process of the system, please take a snapshot at time X. Does that work?
If it's a logical time, then if it broadcasts it to all the processes, then all the processes can take a snapshot of all the events occurred within that time. And the channels can also take a snapshot of all the messages sent less than or equal to that time and strictly received greater than that.
Basically, everyone keeps track of everything, so when you ask me about something in the past, I can tell you what it was.
Say more.
If I keep track of every possible event in my entire computation, and you ask, what happened at X? Well, I have that stored, I can just tell you. And if you ask me what's about to happen at X, I'll just finish my computation, and now I'm at X, I can tell you. Because I just keep track of everything. Very wasteful.
If I log every single non-deterministic event, then I think I can do what you're suggesting. But I'm still trying to figure out how I decide how to coordinate which points in time.
That's the logical clock.
Okay, so let's come back to the logical clock. So if the timestamp that I'm broadcasting is a logical timestamp, and everybody picks something that's causally concurrent with that logical timestamp, then we're okay. Why?
Because it'll still be consistent.
Why?
Because all messages that have been received will be sent.
Because they're causally concurrent, it can't be that I reflect the receipt of the message, but you don't reflect the send. If you sent the message to me, then those timestamps are not going to be concurrent. So by picking causally concurrent ones, that frontier never cuts through messages in the wrong order. That's the way of thinking about it. Can I do it with physical timestamps?
You can do it if your clock's were synced within the amount of time. and the minimum amount of time that it would take for the message to be transmitted.
Exactly. So it turns out that if my clocks are synchronized to less than the one-way propagation delay, then I'm guaranteed that if everybody takes a timestamp at the same moment in time, then I'll never reflect a message receipt that somebody hasn't yet sent, because that message will still be in the channel. Okay, so with tight enough clock synchronization, you can do it at physical time. But we're again coming back to this, how tight does the synchronization have to be? It has to be tighter than message propagation delay, so that it reflects all possible message causality. Is a really cool result.
Slow down.
Didn't we say that our error for synchronizing clocks had at least the minimum delay in it?
Yeah, that's a problem.
So I think we're dead, right?
It turns out that we're almost dead. But in the very back part of Lamport's time clock in the ordering paper, he actually prescribed a way to synchronize clocks by piggybacking on message transport that actually does the right thing. So go back and reread that. What was that you said?
Slow down messages.
Another thing that I could do is bound the rate at which messages or events happen inside of the system in order to do that. We're going to read about that technique kind of in the Spanner paper in a few weeks.
But this time broadcasting technique requires it to be a FIFO channel.
To be a what?
First and first out channel.
It requires FIFO channels for sure, yeah. Okay, somebody walk me through how this snapshot algorithm, Lamport's snapshot algorithm actually works. So it has a beginning, a middle part, and an end part. Let's start with the beginning part. How does a snapshot begin?
Somebody decides to start a snapshot.
Who? And under what circumstances?
Anyone, anytime.
So it could serve an external trigger to trigger a snapshot.
There could be an external trigger, or somebody could just spontaneously decide, I feel like starting a snapshot right now. And how do you actually begin a snapshot?
Sending a marker.
Sending a marker. So the snapshot begins when the first process sends a marker. And we can decide externally however we want to begin that snapshot process. Through a message to you saying, please begin the snapshot, to start it at some physical wall clock time.
Could two snapshots run concurrently?
Well, that's an interesting question. What happens if two processes at the same physical moment in time spontaneously decide to send a marker? Is that okay?
Two snapshots.
It's actually one snapshot. Yeah. It's okay because those snapshots will still reflect causality as those markers will still capture something that's causally concurrent. So we don't actually have to coordinate the beginning of a snapshot. It's okay for anybody to spontaneously, without coordination with anybody else, just send out a marker in order to begin a snapshot. We might want to affix a sequence number on those snapshots, on those markers, so we know which snapshot is running. But you and I could send a token with the same sequence number on it at the same time and everything's okay. It'll still reflect a consistent snapshot. Okay.
So to reflect on that just briefly, if you send it at different times, does that with the same sequence number, does that not work?
It also works.
Also works.
Yeah. The only constraint that happens is once I've received the token, and that constrains my future behavior in some interesting way. Okay.
One part of this I didn't pick out on paper, maybe I just couldn't read fast enough. He seemed to imply that the system was made up of nodes and channels, and anybody could decide to initiate a snapshot.
Mm-hmm.
And the problem I had with that was the topology of the graph was such that that node initiating a snapshot and sending markers down all of its channels wouldn't actually propagate to every node in the network. I don't think you get there.
I think you're right. So one of the assumptions is this is a strongly connected graph, so that starting it at any node, I can follow links to reach every other node. So you have to assume that kind of a topology.
Because their definition of a system didn't have that property.
It did. It was buried in a sentence of the paper, but it was there. You have to assume it's a fully connected topology in that sense.
Is there a difference between fully connected and strongly connected?
Sorry, you're right. You have to assume it's a strongly connected topology.
And if it's undirected, disconnected is fine.
Right.
Yes.
Exactly. Okay, so I begin by sending out a token. When does the snapshot finish?
Tuesday.
42. That's when it's.
You don't know. It depends on how long tokens take to propagate throughout the system. But when do we know that it's safe to gather all of those states?
Everyone told me that they had processed their own snapshot and sent it all back to me.
When the originating issuer of the marker receives the marker.
That's not enough.
No,
So I'm going to send the marker out to all of my locally connected people. They'll send it back to me, but it still might take a long time for that token to propagate to some far-reaching corner of the system. So the sender doesn't intrinsically know when the initiator doesn't actually intrinsically know when the snapshot finishes. So what state must be true for the snapshot to have finished? What sort of condition must be true? Even if no individual observer can see it.
Every node's got the marker.
Every node has received the marker from all incoming channels. So it's not enough to have received the marker once. I need to receive it on all of the channels that show up on me. Because that marker, you can think of it as sort of pushing the channel state into a node for it to record it.
Yes, but when every node gets the marker, it sends it out on every channel. So once every node has got it.
If I receive the marker, I take a local state snapshot the very first time that I've received the marker. And then I send that marker out to everybody that I'm connected to. And I wait for markers to show up to me. While I'm waiting, I'm recording messages that arrive on the channel. I can stop recording once I've received that token from all incoming channels.
You wait to receive only from connected local.
Right, exactly. So here's the way to think about this. I wish I had drawn this picture. But you can kind of think of this beginning process sends this token out to all of its connected peers. And there's kind of this event horizon of these tokens propagating outwards. Then each of those recipients rebroadcasts the token out to all of its connected peers. And that event horizon continues to proceed outwards. So you can kind of draw a line around where all the tokens have propagated. What is that line? This is how to test if you really understand the snapshot algorithm.
So treat span
causality.
Yeah.
Say more.
What's furthest you can get that you would have had influence? You could potentially have had influence.
It's the boundary between before and after. It's the boundary between before things that could not have been influenced and things that might have been influenced. So it is basically causal concurrency propagating outwards into the system. So the way of thinking about this algorithm with the FIFO channels is it's basically pushing these tokens out throughout the system, flushing to disk all of the local node states and channel states that could have happened before this token was sent to the system, or before it's defined causally. That was really deep.
So
probably too deep for 2.5 hours into a lecture.
So you record the messages that you're receiving, but you don't send further messages.
The very first time I receive a token, I record my local state, and I send the token out to everybody that I'm connected to.
Right.
From that point on, all I'm doing is recording messages that arrive.
But not sending anything further.
Right. Until I receive a token from each of my incoming channels. That token tells me when I can stop recording from that channel. And once I've received a token from every incoming channel, I'm locally done with my role in the snapshot. So when is the snapshot globally done?
When every node is done.
When every node is locally done. In other words, when every node has received a token from all of its incoming channels. And that's gotten a chance for that event horizon between before and after to have propagated throughout all of the channels of the system and to flush all of that channel state.
But a single node doesn't actually care about the global snapshot being done. A single node only cares about its peers telling it, yes, I'm done, now you can process my messages and move forward.
So I can locally decide when I'm done with this global snapshot. Can anybody locally decide that the snapshot is done?
No.
So how do we decide if the snapshot is done?
Call the system admin.
And what does the system then do?
Look at the little green light on every single node.
That's basically what has to happen. So independently from the snapshot algorithm, we need to come up with another algorithm for gathering all of these local snapshots. And there's a really simple way of doing that. When I'm locally done, I send all of my snapshotted state to some distinguished receiver. And when that receiver has received those snapshots from everybody, then you've gathered a global snapshot and you're done. Okay.
What if one node fails?
Oh, geez, I'm going to take a drink. Let me repeat that question. So the question is, what happens if node failure is possible?
Snapshot is failed.
How do you know?
You don't know that it's
will keep waiting forever for this node to send its snapshot, and it will not because it's failing. So
well, let's
not be able to acquire the.
Let's not even worry about the termination of the algorithm. Let's just worry about the middle part of the algorithm. I'm going to be waiting for a token from you, and you're failed. How long do I wait?
You either set a limit for yourself for waiting, or.
Oh boy. Okay, so here we go. Here's the proposal. I'm going to set a timeout. And if I haven't received a token from you, I'm going to assume that you're failed. And I'm going to record the fact that you're failed in my local snapshot. Does it work?
So you're no longer recoverable. All you're doing is detecting failure now.
Yeah.
Okay, but what timeout value should I set this to? And what's the penalty for setting it to be too short of a timeout?
You will fail too often.
Worse than that, I will record you as having been failed, but you're not. So incorrectly record the state of the global system.
Your snapshot would have landed in an irrecoverable state too often as a result of that. Because we're assuming that all the snapshots need to arrive in order for the entire system to be recoverable.
But it's worse than that.
So if you record just once that someone has failed, you will not, like in the further snapshots, you will not be sending a marker to that, and it will like.
Right, but in the meantime, that person might not have been failed, and they're continuing to influence the system.
Even though they are not failed, we will not be sending any markers to them, and this will permanently mess up the state of the system.
We might have a channel failure, so two processes will write each other as failed, but actually both of them are active.
And that's a big problem.
Yeah.
Because now my snapshot reflects an inconsistent state of the system. It says that things are failed, but they actually haven't been. Is there any timeout value that I can safely decide that you're failed for?
Oh, there's have a timeout to ping
from Microsoft, say that again?
You can have a timeout to ping the servers that haven't called back and just see if they're still up or not. It would violate your process of like not sending messages, but if you make that message like the format of that deliberately be non-causal, it would still end up effectively giving you a consistent snapshot.
I don't think I fully understood that. Sorry.
I was going to say that if you could ping the servers, like the person who hasn't sent you that message, you could ping them to say, "Hey, are you still awake?" and have that timeout. And if you time out, that keeps.
But how long? But how long do you wait for the ping to come back?
Whatever you have to set some reasonable probabilistic bound.
But it's probabilistic now. What happens if I get unlucky?
A few times, and then you get really unlucky, then so be it.
You roll back to the previous snapshot and start
Well,
snapshot.
this is what I'm saying. You've got two very different constraints that are battling for an answer here. One is theoretical correctness. Would this thing complete if it had infinite time and infinite resources, right? And I don't think in my data center I'm looking for absolute correctness. I'm looking to make sure that the money I'm spending makes sense, right? And so some reasonable timeout, so that my machines can become available for the next job I have for them, I'm okay with that, actually.
Okay, but here's the thing. It's fine to pick a reasonable timeout.
Yeah.
And there'll be some probability that you guessed incorrectly. Therefore, you've got some probability of gathering an inconsistent global snapshot and having unbounded badness as a result.
Yes, and the alternative would be to wait forever to get my investment working for me again.
Exactly. So here's the bad news. If failures are possible, the global snapshot may never terminate. And this is a dual side of an impossibility result that we're going to come back to when we talk about Paxos. Even if a single failure is possible, you can't guarantee that an algorithm that tries to gather some global consensus will terminate. It's because in the limit, nobody can tell the difference between a slow node and a dead node. And therefore, if you declare somebody dead, you might be jumping the gun and they're just that much slower. So the bad news is for this global snapshot to work, everybody has to stay up and act correctly forever.
Which is not true.
Well, which is not true. So what do we do?
I think good enough is good enough.
We set timeouts, and if a timeout happens, then I declare that not only has the snapshot failed, but I can't gather a snapshot because I don't know whether you're up or down. So said a different way, in a real system with real delays and failures that are possible, it's not a guarantee that a global snapshot will succeed. And that's the best that you can do. It might succeed, but it might not.
I think we knew that.
But it's really frustrating that I can prove to you that my system might not terminate cleanly.
If it succeeds, would it be inconsistent?
No.
But what if one node marked the message it sent as not sent because of a timeout or something?
Oh, we can't have any timeouts. That's what I'm trying to say.
So if you have a timeout, then we don't have a guarantee that the algorithm will terminate.
If we have a timeout, then all we can do is declare that the snapshot has failed.
Okay.
What if you could, if you don't receive it by a timeout, you send a self-destruct packet to the node so it blows itself up and maintains consistency?
And how long do you have to wait for that self-destruct packet to show up before you proceed?
Just assume it works.
Might not.
Isn't timing out and declaring that that node failed the same as receiving the message that from that node that I have failed? So
yes.
You are taking a snapshot. You are imposing, right?
Oh.
If you do anything else from that point on, you cross the barrier the wrong way.
Right.
Like we're showing in the diagram.
I think that's right.
Yeah.
And there's some deep results about this that I'm not having you guys read, which is basically papers on. So what I've claimed is if failures are possible, you can't come to consensus. You can't guarantee that you'll come to consensus. It turns out that if you can build a reliable failure detector, then you can come to consensus. But it's impossible to build a reliable failure detector. And that's roughly what you're talking about here.
Isn't like detecting failure a consensus problem in itself?
Exactly. Yeah. Let's delay that conversation for a few lectures. I think that's basically all that I wanted to say. So a lot of this has been really, really abstract. I understand that. But the thing that I wanted you to take away is an intuitive notion of what ordering really means inside of distributed systems. And it's basically that the best that we can do is order things in terms of influence or potential influence. So later on when we're talking about replicated systems and trying to decide on the order in which writes happen, a common constraint that people end up doing is deciding to order things to respect causality. That'll end up being the strongest that we can do in a lot of cases. So let's wrap up there, and I will see you in a week. Remember that homework 1 is due on Monday.
Where do you ping the server?
Oh yeah, the server. Let's take a look at the ping. Give me 1 minute. Sorry. I'm sure you're all dying to know what the histogram looks like. What did I call it? Yep, and it's number of, oh yeah. So it's hard to see the histogram because it's so long. But here it is, coming up over here. and then an incredibly long tail, exactly as the paper predicted. So the median latency is probably on the order of about 3 or 4 milliseconds. But there's this incredibly long tail where we actually saw some measurements that were more than 200 milliseconds here. If we kept running this, this would get harder and harder to spot because that tail would get larger and larger. That's exactly what we're talking about. That's a real measurement from a real system, unbounded delay, which is kind of cool.
Graph that in a log in the vertical?
I don't know how. I could, but I don't know how. All right, we'll see you in a week.